Okay, let's dive into this. Something really caught my eye this past week. It was an announcement, April 26th, from India's Ministry of Defense. Seems the DRDL Defense Research and Development Laboratory made a pretty big step.
Yeah, I saw that. The subscale Scramjet engine test,
Exactly. They ran it on the ground for over 1,000 seconds.
which is, well, it's huge when you think about it.
Right, because back in January, a similar test only managed, what, 120 seconds?
120. So this is, well, it's nearly an order of magnitude longer.
Yeah.
A massive jump in endurance.
So what does that actually mean, this longer duration?
Well, it really points towards India seriously leveling up its game in hypersonic missile development. That's a field, where everyone's competing hard.
And right now, only Russia has an operational air-breathing hypersonic cruise missile, correct?
That's the state of play, yes. So this Indian test is very significant contextually.
Okay, so for this deep dive, let's try and understand what this scramjet progress really signifies for India. For their tech capabilities, especially advanced missiles. We'll look at this test, but also the backstory, the programs leading up to it. Our source for this, by the way, is a recent report in the Eurasian Times.
Sounds good. And it's important to remember this didn't come out of nowhere. This builds on years of work, particularly the HSTDV program.
HSTDV, right? The Hypersonic Technology Demonstrator Vehicle.
Exactly. Led by DRDL, which is DRDO's Hyderabad lab.
So the HSTDV was kind of the foundation for this.
You could say that, yeah.
Yeah.
It laid the groundwork. The main goal there was to demonstrate sustained, autonomous hypersonic flight using an air-breathing scramjet, crucially, fueled by kerosene.
Kerosene, so relatively common fuel.
Right. Makes logistics simpler down the line.
And the HSTDV itself, what did that look like?
It was basically a cruise vehicle, the CV, perched on top of a standard rocket booster, the LV, and had fairings, protective covers for the initial launch phase.
Okay, so how was it supposed to work in flight?
The plan was the rocket booster, the LULA, would shoot it up to about 35 kilometers altitude and get it moving really fast, up to Mach 6.5.
Mach 6.5. 6.5 times the speed of sound. Wow.
Extremely fast. Then up there, the cruise vehicle would separate from the booster, jettison those fairings, and then ignite its own scramjet engine.
And the target for that scramjet burn?
The initial goal was about 20 seconds of sustained flight at Mach 6.5.
Just 20 seconds? Seems short compared to the whole 1,000 we just talked about.
Well, yes, but back then, even achieving 20 seconds of controlled scramjet flight at that speed was a huge technical hurdle.
So did they manage it? Did the HSTDV test work?
Oh, yes. Back on September 7th, 2020, they had a successful flight test. And interestingly, they actually achieved more than the targeted 20 seconds of scramjet-powered flight.
Ah, so they exceeded expectations even then.
They did. It was a really strong validation of India's capabilities in this whole hypersonic arena.
Okay, but flying hypersonic, above Mach 5, it's not easy, right? There are some major challenges.
Oh, absolutely formidable challenges. It's not just about going fast. One of the biggest is just the heat, aerodynamic heating.
Friction from the air at those speeds.
Exactly. It generates incredible temperatures in the vehicle's surface. We're talking potentially over 2,000 degrees Celsius.
2,000 degrees. Okay, so you need materials that can just survive that.
Precisely. Advanced thermal protection systems, exotic materials, that's essential.
What else?
Then there's combustion. Inside the scramjet engine, the air is still moving at supersonic speeds. So you have literally milliseconds to inject fuel, mix it with that super fast air, and get it to burn stably.
Milliseconds? That sounds incredibly difficult from an engineering perspective.
It is. It requires incredibly sophisticated fuel injection and combustor design.
And controlling the vehicle must be tough too.
Definitely. Managing the aerodynamic drag, the shock waves that form around the vehicle, it all needs very precise aerodynamic design for stability and to ensure the engine actually works efficiently.
So the HSTDV program, it tackled most of these.
It did manage to overcome most of them for that short duration flight. But the big one, the real sticking point for longer flights, was dealing with that intense heat buildup over time, the sustained frictional heating.
Right, because that 20-odd seconds for HSTDV is one thing, but an operational missile, like Russia's Zircon you mentioned, needs to fly for minutes, right? Not seconds.
Exactly, several minutes, potentially. And enduring that level of heat soak for minutes requires a whole different level of thermal management.
Which brings us back to the latest breakthrough. How is DRDL tackling that sustained heat problem?
Okay, so this is where it gets really interesting. They're focusing on two key technologies based on the reports.
Yeah.
Active cooling systems and advanced thermal barrier coatings, TBCs, particularly in the combustor.
Active cooling, what does that involve?
The basic idea is you circulate a coolant fluid through tiny channels built into the walls of the hottest part of the engine, the combustor.
Okay, like a radiator in a car, but inside the engine walls?
Sort of, yes.
Yeah.
And often the coolant fluid they use is actually the fuel itself, the kerosene-based fuel.
Using the fuel as coolant. How does that work?
As the fuel flows through these channels, it absorbs the intense heat from the combustion chamber. This stops the metal walls from overheating, maybe even melting.
Clever, so it protects the engine.
Yes, but there's a double benefit. This process preheats the fuel before it's injected into the combustor.
Ah, and preheated fuel burns better.
Much more efficiently, especially under those high-speed airflow conditions. It's called thermally regenerative cooling.
Thermally regenerative. Okay, so it
Wow.
solves the cooling problem. A&D improves engine performance.
Precisely. It's a really critical piece of the puzzle for making operational hypersonic cruise missiles viable.
Got it. And the second technology, thermal barrier coatings, TBCs.
Right. TBCs. Think about the conditions inside that combustor. Air rushes in, gets compressed, heats up massively, like you said, potentially over 2,500 degrees Celsius even.
Yeah, brutal environment.
Extremely. So you need to protect the actual metal structure of the engine from that direct heat. That's where TBCs come in. They apply a special coating, usually a ceramic material, to the inner surfaces.
Like painting a heat shield onto the inside walls.
Essentially, yes. It acts as an insulating layer. It drastically reduces the heat that gets transferred to the metal parts. And it also protects against oxidation and corrosion, which happen much faster at those temperatures.
So the TBCs basically help the engine survive longer.
Exactly. They extend the engine's life and reliability, making long-duration flight possible. Without effective TBCs, the engine would likely fail very, very quickly under sustained hypersonic conditions, catastrophically.
Okay, so active cooling using the fuel and TBCs for insulation. Makes sense. Did this 1,000-second test involve anything new with the fuel itself, apart from using it as coolant?
Yes, apparently so. To make that active cooling really work well, they needed a specific type of fuel. It's called an endothermic fuel.
Endothermic? Meaning it absorbs heat.
Exactly. This fuel is designed so that as it flows through those cooling channels and heats up, it undergoes chemical reactions before it even gets injected to burn. These reactions, a controlled thermal decomposition, actually absorb a significant amount of heat energy from the engine walls.
Wow, so the fuel isn't just passively cooling, it's actively absorbing heat through chemistry.
That's the idea. It adds another layer to the cooling process, protects the engine structure even more effectively, and also sort of pre-processes the fuel, making it ready for very efficient combustion.
That sounds incredibly advanced. Did DRDL develop this fuel?
Yes, the reports say DRDL developed this endothermic scramjet fuel in partnership with Indian industry, and its successful development was crucial for achieving that 1,000-plus second ground test.
And I imagine making this stuff isn't straightforward.
Probably not. They mentioned needing a specialized manufacturing process to produce it at scale with really tight quality control.
Okay, and there was one more thing. An advanced ceramic TBC. What's different about that?
Right, so beyond the standard TBCs, it seems DRDL, working with a lab under the Department of Science and Technology, DST, has developed a next-generation version. This one is specifically tailored for the even harsher conditions of sustained scramjet operation.
Even more heat resistant, presumably.
Yes, designed to withstand higher temperatures and greater thermal stresses for longer periods. And they're using specialized techniques to apply it to make sure it sticks well and provides maximum insulation and durability.
So better coating, better fuel, better cooling. It all adds up.
It really does. Each piece is vital for pushing that flight duration envelope. This advanced TBC is positioned as a key enabler for truly long-duration hypersonic flight.
So putting this all together, where does this place India globally? We know about the BrahMos II collaboration with Russia. Is this new scramjet tied to that?
That's the million-dollar question, isn't it? The link isn't explicitly stated. India and Russia are definitely working together on BrahMos II. But whether this specific DRDO-developed scramjet is destined for that missile, it's not clear right now.
But it's possible. Maybe down the road.
It's certainly plausible. Developing this capability domestically gives India options. Potentially, this indigenous engine could replace a Russian one in BrahMos II in the future, which would be a big step for India's self-reliance, its Atmanirbhar Bharat initiative in defense.
Makes sense. And that Russian collaboration must still be valuable, right, given their experience with Zircon?
Oh, undoubtedly. Russia has demonstrated capability in areas like vertical launch for hypersonic missiles, booster integration, complex guidance and control systems. That know-how is incredibly valuable, and India likely benefits significantly from the partnership, regardless of the engine source.
Okay. Now, India is also working on its own long-range hypersonic missile, the LRHM. There was a test last November.
Yes, November 16th, 2024. A successful test of a missile with reportedly over 1,500-kilometer range.
Is that using a scramjet then? This new tech, maybe?
Well, this is a really important distinction to make. The official press release about the LRHM test, it made no mention of a scramjet engine.
Oh, so what does that suggest?
It strongly suggests the LRHM, at least in its tested configuration, is likely a boost glide vehicle,
Boost glide.
meaning it's boosted to high altitude and speed by a rocket. Then the payload separates and glides unpowered towards the target at hypersonic speeds.
So different technology pathway compared to an air-breathing scramjet cruise missile.
Exactly. Both are hypersonic weapons, but they work differently and present different technical challenges. The recent 1,000-second test is specifically about the air-breathing scramjet propulsion needed for cruise missiles.
Got it. So let's circle back and summarize. The big news is this very long ground test of the DRDO scramjet engine.
Absolutely. Over 1,000 seconds is a major milestone. It really puts India firmly among the leading nations developing this kind of hypersonic missile technology. And crucially, it signals a move towards greater self-sufficiency in a really critical strategic area.
And the potential spin-offs from mastering these technologies, materials, thermal management, could be huge too, right?
Definitely. Advances like these often find applications far beyond just missiles. Aerospace, energy, potentially other high-tech industries could benefit. It gives India a broader technological edge.
And it was enabled by cracking some really tough problems. The active cooling, the advanced TBCs, that special endothermic fuel.
Exactly. These aren't minor tweaks. They are fundamental breakthroughs needed to overcome the barriers to sustained hypersonic flight.
Which leads to a bigger question, perhaps, for you listening. Thinking about India's strategic goals, its push for self-reliance, what do you think are the wider implications here? As India keeps pushing these hypersonic boundaries, how might this reshape its defense posture, its influence? Something to ponder.
Absolutely. And for those of you preparing for exams like the UPSC, this kind of deep dive understanding these specific technological strides by India using sources like the Eurasian Times, it's really vital. This touches on current affairs, science and technology, national security, all key areas.
Definitely. So if you found this breakdown useful, please do give us a like, subscribe for more deep dives, and definitely leave a comment if you have more questions or want to discuss this further. We'd love to hear your thoughts.
Yes, please do.
And just to reiterate, our main source for today's discussion was the Eurasian Times.